Alright, welcome to my DE10-Standard FPGA tutorial. This is the number 4. We have totally 5 videos, and the 5th one will be a demonstration. I will pretty much walk through the design of my demonstration design and also give you some measurement of my actual system, how it runs. And in terms of tutorial and actually learning something, this is the last video. So last time in the 3rd video we played with the official FPGA image from Terasic, and this time let's create our own image. Let's get started. So the tool used to call Qsys. It used to call SOPC Builder, and now it's called Qsys, and that is the tool we are using to build our system. So generally, if you want to start a project, you open quarters and create a new project. But this time, let's do a different way. So Terasic is kind enough to provide a tool called System Builder. So because if you want to build your own FPGA system, you probably have a lot of pin assignments, and if you assign a wrong pin, you probably will fry your chip, or something will just not work, or some weird reliability issues or whatsoever. So if you can have an automated tool that actually does all the pin assignment for you, that will reduce a lot of chance for having some error. So in this case, they provided this tool, and they generate a quarters template, and that's basically what we're going to do. So let's call the project demo LED. I want to have the LED, and I want to have the clock. I don't care about these features. And since I'm using Qsys, I want to have the HPS. I don't care about the GPIO, I don't need the HSMC, so that's it. The name, the peripherals, and the hard processor system. So keep in mind that this SDRAM means this chip. So that's a SDR SDRAM. It's not the DDR SDRAM. The DDR are these chips, and they're controlled by HPS. Alright, so that's it. Let's generate. Let's put that on desktop. Let's create a folder. Demo LED. Save it. Alright, now we have our generated project template. Let's open the project file, and you will see a Verilog template that has all the required GPIO pins. And also there will be some constraints when you are doing the pin assignment. They do all of that for you. So we can strip the design. The provided template has 4 clock inputs, and we only care about 1 clock. It has 10 LEDs, but we only need 8 of them. Well, you can use 10, but in this case I just want to use 8, but you can use 10 of course. That's the USB fee, that is the UART. I don't need the SPI interface, so I can get rid of all of them. I need the SD card for boot up. I don't need external reset. I don't need these things. I can remove all of them. G sensors, LCD. I mean the 128 by 64 monochrome LCD. I don't need a flash chip. I already have the SD card, so this is another flash chip. I don't need this one. I do want to have Ethernet. I do want to have DDR3, and that's it. The first pin is actually controlling the USB to UART bridge chip, and I believe that's a reserved pin, so I can remove it. If you want, you can keep it, but I just want to get rid of them to get a bare minimum system. So, alright, let's save this file, and let's fire up Qsys. Tools, Qsys. We're going to create a new Qsys file. So let's call that HPS. And let's add the main processor and peripherals, hard processor systems, and Araya 5 Cyclone 5 HPS. Let's double click that. So there are a lot of things to configure in, especially for the DDR timing things. So I will just copy and paste the data from the reference design. So let me open the reference design. Where is that? We'll open that in another window, in another screen, so you cannot see that. But I'll just simply copy and paste the number, so I don't have to split the monitor. Let's go to Qsys. Yeah, that's the reference design. It has a lot of bells and whistles which I don't need, and you will see there's a lot of things, and I will pretty much only add very bare minimum things to do the demonstration. So there will be quite some difference, but anyway, I only need the numbers. Oh, by the way, there's upgrade IP cores because the reference design was generated using quarter 16 and I'm using quarter 17. Let's first dismiss this thing. They have their HPS, SDRAM. That's what I'm going to copy. Let's put this aside. Okay, let's go back to our Qsys. I don't care about these signals. I don't need the normal FPGA to HPS or HPS to FPGA bridges. I only care about the lightweight. That's the one we're going to use this time. And I already have the DDR, so I don't need SDRAM. Let's move it. It takes some time to respond, but anyway. I don't care about the interrupts exchanging between HPS and FPGA, that's fine. The peripherals, I will just copy the configure from the reference design. So I'm using the first Ethernet in reduced GMI 2 mode. I don't care about the NAND controller, I don't care about the QSP, I already removed the pins. I do need the SDMC for boot up. And 4-bit parallel mode. I will use the second USB controller using the set 0 pins. And the clock output mode, correct. SPI controller, I don't need that. And UART, I'm going to use the UART. I'm going to use the first UART and the first set of I/O. And I don't have a flow control pins. Okay, I don't need the I2C, I don't need the CAN bus, I don't need the trace port. Alright, and finally, according to the datasheet, there is one open drain output from the reset chip to the Ethernet controller, and that's gonna be used by the driver. That's gonna be GPIO 35. So I will export this GPIO. Okay, so we have exported this GPIO. I have set the proper peripherals. That's done. And then let's go to clock. These are both 25 MHz, regardless the bus clock, which is 50 MHz. That's correct. I don't care about this. And up clock. Let's see. I want to run maximum clock, and this is correct. It's correct. These are both correct. Correct. 100 MHz, 100, and 200, 400. That's the MMC USB clock. So everything's fine. All right. Then the tedious part, the SDRAM. You might have noticed that whenever I change anything, there will be a delay because the system tries to validate everything. So you will see there are a lot of things to change, so feel free to skip this part. That will take a lot of time. Alright. See that? It's stuck there. And only now can I edit anything. 25. It will take some time for it to update. What happened? Okay. So we're using Micron chips. We are using 32-bit bus. That's actually two 16-bit devices. So it's going to be 4 groups. And 15 row address and 10 column address. Alright. And the CL is gonna be 11. And we have this. Let me see what are the, yeah, and the right CL is gonna be 7. And besides that, I think everything should be okay. And let's move to memory timing. So here's a lot of difference. Minor differences, but takes a lot of time to edit. 40, 30, 65, 125, 0.38 to 55, 0.25, 0.4, 0.2, oops, that's gonna be 0.4, 0.2, 0.2. 500, 4, and 35, 13.75, 13.75, and 7.8, 260, 15, 4 cycles, 45, 7.5, 7.5. So that's correct. Let's go to board setting, default setting, and here's the board skills. That's the routing mismatch. So in this particular board, we have 0.03, 0.02, and 0.06. And we have 0.12, 0.01, and 0.06, and 0.05, 0.02, and 0.01. So that's the HPS block. Should be fine. And we want the HPS to be the master reset output, and it resets the main bus clock, and the bus clock resets everything else. So we click the reset output and click this button on the reset input, connects them together, and the clock output will be clocking the Avalon or AXI bus. And that's pretty much it. And let's add some peripherals. So this time, last time we blinked one single LED, and this time let's say we have 8 LEDs. So how about let's run one LED at a time, and from left to right, and then go back. So a looping LED pattern. So let's add a parallel I/O. Let's add something. Parallel I/O bus. Right, we have 8 LEDs. I want them to be output mode. It can be in-out mode or output mode. And if for in-out mode, you have to configure them to be output for the GPR peripherals. And for the output mode, just write the peripheral and just write to that particular bit, and you can set the output. So the output mode is easier to use, but you cannot read from that. Later we'll see the difference. So if your program is, let's say, if you write your program in this fashion, I actually have the code already prepared. So now the LED is actually the address of the particular LED peripheral, which is the PIO peripheral. So if you want to do, let's say, if you want to do this kind of trick, so you are reading the value and shift that and writing that back, so you have to set that to in-out mode. If you want to set that to output only mode, this won't work because you cannot read anything from the register. So that's one thing to keep in mind. But if you use another variable to store the status and you only write to this particular address, then it doesn't matter. So in this case, I will set output, and default all the LEDs are off. The particular board is designed so that the LEDs are active high. So you set them to 0, they are all off. 8 bits output mode, and I think everything's set. We can finish. And we give it a more sensible name. Okay. And the same thing, the reset comes from the master reset. So the HPS resets the clock resets everything else. And in this case, this is the only peripheral on the bus. But if you have more peripherals, they all come from the LED reset. Of course, you can just reset it from another source or something, but I prefer to do this. Okay, and the main clock is also clocking this peripheral, and also the bus. They're sharing the same clock. And the slave port goes to the master port of the main processor. So you see, this is an AXI bus, and this is the envelope memory map bus. So in between there should be a bridge called there should be a pipeline envelope bus memory map bridge, and you can explicitly add them, or you can just leave it there, and when you're compiling the Qsys project, Qsys will actually automatically insert whatever bridge converters that's going to be needed. So I will just leave it this way. So of course we have a parallel I/O bus. I want to export the I/O bus. We double click that, and we export this. Just call LE external connection, whatever name you want to name it. I will just leave the default name. And the clock must be externally provided. That's correct. And let's double check the HPS. The master clock is gonna be 50 megahertz. It's not here. It's gonna be the master clock. 50 megahertz, correct. So I think everything's fine. Let's save this project. Now let's generate the HDL. Generate. Will take some time, but fairly fast actually. This process compared to the final synthesis and place and route, this kind of things. We'll finally compile the entire project. Will take somewhere like 4 minutes. That's a very tedious process. And because I don't have a professional subscription license, so it won't use all of the CPU cores of my computer. I have 22 cores and 44 threads, but it will only use 1 core maybe. Well, Quadros is not really a cheap software, so I'll just use the free version. It will take some more time, but anyway, yeah, you can see here it actually has the interconnect bridge inserted for us. Okay, and we need to actually put the generated HDL block into our top level design. So let's say show instantiation template. Copy that, and let's paste it. So that's our HPS block. Let's fill in the blank. And before we do that, let's add the generated Qsys. Alright, click OK. So now you can see we have the Qsys and also we have the top-level design. Oops. It's a hierarchy. Let's fill in the blank. The clock goes to clock. This will take some time. Feel free to skip. It will take quite some time. So the DDR part, address bus, bank address part, clock part, and the other clock. That's a differential pair, and clock enable. Where's CKE? And chip select. We have the row assertion and the column assertion. So where is Qsys and res? Okay, it's the Qsys. And the res. Write enable. Reset. And data bus. DQS. Complementary. On determination. Where's ODT? Data mask. And the RZQ. So that's the DDR3 part, and then we have the Ethernet controller part. Let's go to transmitter clock, transmitter data. So whatever reason it's not actually exposed as a bus, it's just individual bits. So I have to do it this way. And the receiver data. And we have the MDIO, the configuration bus for the Ethernet transceiver. MDC, MDIO, that's pretty much glorified I2C bus. I believe so. There is the recovered clock. The recovered clock goes here. And transmitter enable. The receiver data ready, data valid. And I think that's the Ethernet controller, and then we have the SD card controller. So SD clock, SD command, and SD data. So SD clock, SD command, and we have SD data. D0, D1, D2, and D3. Now we have the USB ULPI and UART port. So the UART goes here, receiver goes to receiver, transmitter goes to transmitter, and the GPL35 goes to the reset pin of your Ethernet fee. This is actually indicated on the schematics. And now we have the USB port. Data bus, tedious 8-bit data bus. And we are done. Okay, so now we have a top level design. Let's check we don't have any typos or something. We don't have anything that LDR 50, LDR 50. Alright, that should be good. Let's save this file and let's analyze this Verilog file. This should be fairly fast compared to full synthesis. So the goal is to let Qsys know the I/O port declared and assignment. So now it knows we have the HPS module, it knows we have all the pin setups. That's good. See that interconnection inserted between the AXI bus and Evident bus. There's a bus translator, correct? These are all Qsys job. Now we're finished, and we can do the assignment. Before we do that, when we generate a system in Qsys, it actually also generates some scripts that can help us to do the pin constraint. So let's use these scripts to go to Tool, TCL scripts, and in the HPS folder submodules we have the parameters and pin assignment and a lot of other TCL scripts. So in this case we only care about the parameters finished and the pin assignment. Will take some time, but let's see what's the trouble. It always gives me some trouble. Let's see what's the trouble. I don't know what's happening, but let's do a full compilation and see. Sometimes we'll do a full compilation. The Qsys will know exactly what you're doing your design, will know exactly all your connections, and you do the pin assignment once again, that won't give you any trouble. Some weird behavior. It will take somewhere like 3.5 minutes, so that will spend some time, and meanwhile let's do some other things. So because we're going to write some program, and the program will need headers, and the headers are generated from our Qsys. So Qsys will generate a file called the SOPC info, and this file will be used to generate our headers. So to generate a header, you can call a script, and Terasic is kind enough to provide that script in their reference design, and I copy that generate here. So let's open the file. So simply calls a function provided by Qsys, the Qsys EDS, and it reads this input and generates the header output. This command must be in your path. So you have your system variables, and one of them is path. That's where the command line interpreter finds binary programs. You have to make sure this the path for this thing is in the path variable. You can find in my particular installation I put it here. So this is where you can find all of the programs. So let's add this thing to the to our system path. Copy the path, and we go to advanced system setting, environment variables, and there should be a path somewhere. Yeah, path. And you can see here I already did that. If I don't, then you will have some trouble running that script. So make sure that's there. And let's fire up EDS. Demo. I can see the files, and you can see they generate. I will run that. Let's see what's the problem. Okay, right now we can run the script. Right now we can run the script. Finished. Fingers crossed. Fingers crossed. Finished. Okay, this time it runs properly. Okay. So now we can do the synthesis once again, but before we do that, let's do this. So here, beware, be very careful. That's a bug of Qsys. When you try to assign the default pin behavior, I want to change them from pull up to tri-state without any polling resistors. To do that, you have to go to the assignment and devices, and there will be a button say the device pin options. But if you use the design generated by System Builder, it will automatically reset the device to the default device. So that's the trouble. That's a big trouble. If you click OK, then your entire project will be in trouble. So you have to correct this. You have to correct this. So this is the proper device we're using. FC6D6 F31C6, correct. And device and pin options, unused pins. Let's change from the default weak pull up to completely tri-stated high Z. Click OK. OK. And now we can do this process once again. And by the way, in your pin planner, this is already set by the System Builder. I mean the Terasic tool, and these are already set by the Terasic tool. And these are non-used pins, and they will just be dismissed. You can manually delete them, or you can just leave it there. I don't really care about that. Well, let's just delete that. Pin planner. Let's remove these unused pins. So I don't really care about these pins. I don't really care about these pins. I don't really care about these pins. Okay. And I only care about single clock, and the rest I don't care about these clocks. And I only have LED 0 to 7 used, so 8 and 9 they are extra pins. So now we don't have any superfluous assignments. Okay, alright. Now we can do this process once again. Hopefully this will be the last time we do this. And meanwhile, since we already generated Qsys, let's see if this will work. Generate. So now we're creating a macro file. That's pretty much the header. And let's go back. So now we have this thing. So all we care is the base address. In this case, it's just 0 because if you open Qsys, you will see address map, and the LED PIO device is just at 000 address. And if you have more and more devices, you will see they have different addresses. In this case, when we have a single device and we never manually assign the address, so that's why we have the 0 address, which is perfectly fine. So in the meantime, let's write the program when it compiles. I've already prepared a template for this thing. So I just copy the generate, and later we will convert the 0 programming file to the raw binary file, the compressed raw binary file, which is the file format we are going to load from Linux kernel or from U-boot to the FPGA. And we have a make file to compile this program and the just generated header. So the header and the program will be compiled. So let's copy these two things over here. And the make file is really simple. It's pretty much just calls compiler and set the device optimization and input-output files and strip the extra symbols. It's fairly simple. And keep in mind, if you use the SOCL library, the hardware low-level interface library provided by Altera, you have to include that path. But in this case, we're just writing memory directly. We're not using any of the libraries, so I didn't include that include path. Let's see. It's still working. So the main program. Just like every other C program, we have the stdio, std library, stdint. stdio is there for printf and this sort of things. And std library is for exit. stdint is for uint32-t. fcontrol is for these constants. And signal is for handling the control C, and sysmn is for mmap and monmap, and HPS underscore 0.h is the base address of our LED peripheral. And here we define two other addresses, the rec base and rec span. That's the base address of the lightweight host to FPGA bridge. That's the base address in HPS address space, and the span is the size of that particular memory space for lightweight H2F bridge. So when we first fire up the program, we try to open device memory. So let's try to open the entire memory space, and then we try to map the particular lightweight bridge to a certain address. So as you can see here, we previously defined a base address. That's the base address of the lightweight bridge. And we map the particular size and read and write, shared mode, and the FD is the file number we just opened from open the device memory, and that's the base address. That's what we care about. So the base will be starting from this address all the way to this address. So that range is what we can access. And then base address plus offset. The LED base is the offset of your LED PIO device. In this case, it's just 0, but if you have more devices, they will have different numbers. So now you can simply, by writing a number to this address, you can control the LEDs because that is a memory map device. There's no synchronization, whatever things. You just write a number to that particular address, and that controls the registers. And initially, we set LED to the first LED to turn on, and then we use a simple shifter. We use a counter. We use an iterator into I, and we pretty much shift them from the first bit, second bit, third bit, fourth bit, all the way to to the 8th bit, and go around. As I said before, you can also use this trick, and this trick will not work because you can only write to that particular register. You cannot read from that particular register. So you have to use a variable to remember the current position of the LED. That's why I have the iterator here. So that's pretty much the program, and it's always a good idea to free whatever resource you opened, unmap the memory, close that. We hit Control and C and turn off the LEDs. Alright, that's basic cleanup, and I hope we're finished over here. We don't have any errors. Great. So we generate the raw binary file from SOF. So this is also a script provided by Terasic. We run this particular program. We read in this SOF file. Let's say what's the name. In this case, it's called demo-led, and generate an output. So the output file must always be sock-system. It always must be this because the U-boot expects the exact file name. Later we'll see that in the U-boot configuration. Let's run this. Finished. So now we generated a compressed raw binary file. Okay. So let's dump this to the FPGA. Yes, I have the card. So first, let's copy this file, and that's the previous one. Let's remove that one. Let's paste it. And keep in mind, this only works for the console version of the Linux. If you use the LXD version, it will not boot because it expects some other devices. As I said before, it pretty much expects a lot of other devices on the AXI bus, which we don't have. We have a fairly simple Qsys design. So in this case, we have to use the DTP provided with the console version of the distribution. Alright. This is one way we can load our bit stream to the FPGA that's on U-boot, or as we demonstrated last time, we can use the config fs, or you can simply plug in a cable into the pipe blaster and just load FPGA from a Quarters programmer. And that's pretty much the 3 major ways to do this. I will just use U-boot to help me doing this. And let's boot up the FPGA. Let's see what will happen. Alright, let's boot up the system. Oh, before I do that, let's open the console. Okay, it used to be a 5-second delay, and I removed that delay I modified that to 1 second. And you can see the FPGA has been reconfigured, so all the LEDs, they don't have the pull up anymore, so they are completely dark. That's normal. That means our configuration bit stream has been loaded to the FPGA. And I removed the password so I can direct SCP to and from the board. I still didn't figure out how to SCP into this board with the password, so I have to remove the password using password -d. And let's get an address. So now we have 2.32. Alright, so let's go back to EDS. And since we already have the program and the make file and the header, so we'll just compile. Just hit compile. Alright, so now we have the binary generated. Let's copy that. .32. So now we have the file. Let's go back. So now we can see the LED. Let's run this program. Oops, it didn't work. It didn't run as expected. What a bummer. Did I screw up something? Wow, that's not expected. Wow. Start from 0. Oh. I supposed to remove this line, but I actually removed the wrong line. I removed this one. So, oops. Now it should work. Yep, you can see that it runs properly as designed. So I hope you enjoyed this video. This is a fairly simple distribution walkthrough the entire Qsys environment. So we first started with a simple FPGA project, forget about the HPS and configure the boot switch to AS mode. And then we try to download program from directly from Byte Blaster to the configuration SRAM or to the EPSS device. So pretty much use that as a normal FPGA. And then we try to use HPS only feature. So we use the FPGA image supplied by Terasic, and we explore some of the features just on the programming side. And this time we did pretty much put them together. So first we create in Qsys, in Qsys, we design the entire HPS plus FPGA collaboration system, and we write some program to control the FPGA peripheral, which in this case is the LED. So if you run the program, you will see that when we're writing to a particular memory address, we're controlling the LEDs. So that's it. And next time we're going to design a real system. So hope you like it. Subscribe if you like it, and thumbs up. Thank you.